Hi, I'm Mark Weitzman. Welcome back to the final video on the easy way to solve this final problem for and what the professors intended, what a lot of us missed. I know I missed it. I went down a rabbit hole, miscalculated, but finally found my way out. So here we're going to just do the easy way. The easy way is just based on starting with what the information they gave us. You can, at first when you look at this, when you think z is very large, you're thinking, well, this is minus z cubed to the 1/3. So that's about z, maybe with a minus sign because of this branch. So we get minus 1/2z, which is in fact what you get here. You got a little phase. But it's very easy to integrate the function 1/z over a circle. So the easy way to do it is to draw a very large circle so this 1 doesn't matter and we can make that approximation. That's what we're going to do here. So let me draw for near the final time at least our starting points. We've already established that whatever poles there are, on whichever sheets they are around here. So, the easy way to solve this is to close the contour. Our integral is this. So this is our integral, C. Well, let's close it in a big circle. I'm not very good at drawing circles. And make use of the asymptotics on that circle. Now, first thing to realize is when this circle is very big, all of these branch points are at the same point and they're all at the origin relative to the circle. So when we consider phase things, this goes out here. Let me add one more thing. Imagine we go like this, and then we go like this. Okay. Let's evaluate the integral of this function on this contour. Well, there are no branch points. You know, the branch point is over here. So there are no branch points in here and there are no poles in here. So the integral around the whole circle contour is equal to 0. So this tells us that the integral over c of f of z dz, remember c is this part, like that, is equal to the integral, I'll call it the circle right now, let's call it circular arc, going in this direction, because we reversed it, this plus this equals 0. So now we need to just calculate the integral along this circular arc. Okay. Let's redraw this a little bit. I promise you this will be my final time I draw this diagram. So we have our origin like that. Running out of pens here. We have our branch point. Well, we have the branch from the contour like that. And we have our function And we have our big circular arc. Okay, this branch point. The arc's not at infinity. We're going to take the limit as we go to infinity. Right now, for instance, we only go from like here to here on our contour, but eventually we want to go to infinity. So you have to think of this as being a simple calculation and then take the limit as rho goes to infinity. So let's say we have a point on this arc here. Doesn't really matter what sheet it is. Let's this angle be phi. So we have z is equal to rho e to the I phi. And we're going to integrate from this point to this point. That's our circular arc. Now, how much phase do we build when we rotate our usual function, which starts out at here, you know, our z reference? Well, you can see at infinity that this thing rotates from here to here. So we get 4 pi over 3. And everything, all of our branch points are basically at the origin. So we're just going to get 3 times 4 pi over 3 is our phase. Oh, let me, no. I misspoke there. We rotate from here to here. Let's call this angle theta. So when we rotate the first one from this branch point, we get theta. From the second one, we get theta. From the third one, we get theta. So we add them up, we get 3 theta. Then we divide by 3 for the cube root is equal to theta. So this is our phase shift at any point in the complex on this arc, which goes to infinity. And we have that theta is equal to 2 pi over 3 plus phi. In other words, we go from here to here, this is 2 pi over 3, and then we add phi. This is phi. Okay, so now let's write out our integral. So we have the integral over the arc. The arc goes from phi is over here, it's minus 2 pi over 3, and over there it's 2 pi over 3. dz is equal to rho I e to the I phi d phi. So now we get I rho e to the I phi d phi. Now what's our function at the bottom? Well, remember we had our starting phase, which was always minus 1 e to the minus 2 pi I over 3. Now we multiply that by e to the I theta, and we subtract z, which is rho e to the I phi. Okay. Now let's substitute for theta, and we get the integral of minus 2 pi over 3 to 2 pi over 3 I left out something here. I know I did. There's a rho here. This is the rho is the asymptotic value of this, which is the absolute value of z, which is just rho. So I'm going to get I rho e to the I phi d phi divided by minus 1 e to the minus 2 pi I over 3. Then I have e to the I theta. I'm substituting theta is 2 pi over 3 plus phi. Now I have minus rho e to the I phi. Now, First thing you see is that this phase cancels with this phase. That's good. And then you see that rho e to the I phi is everywhere. So we're left with the integral from minus 2 pi over 3 to 2 pi over 3 I d phi divided by, I'm going to put the minus sign on top, and then we've canceled everything. We just have 1 plus 1. Okay. So this is just equal to our contour integral, the integral over c of f of z dz is equal to 4 pi over 3 times I times minus 1 divided by 2, which is equal to minus 2 pi I over 3. So we got the same answer, and we did it about 10 times quicker. The key thing is to recognize that as z goes to infinity, this over here is just going to be an absolute value of z times the phase. So thank you very much for watching these videos. I plan on making a few more, doing about the course itself. This 1.1x was 6 weeks long, and there were like 10 problems each week. And I think I'm going to select one problem from each week, so it's like 6 weeks. So I'll select 6 problems and work them out. They're not all, most of them are much, much easier than this, but there's a few that are interesting, and I'll work out those. Thank you very much. Bye-bye.